Hello everybody. The topic of today's discussion is digital twin, and I will walk you through a few industrial cases. So the presentation is going to take you through a short introduction of Ansys digital twin concept, how we generate different digital twins, and we will also look at industrial examples. Some industrial examples will be a bioreactor case, a heat exchanger case. The answer to what is a digital twin is actually within its name. It's essentially a mirror image or a replica of the physical asset that is in operation. The numerical model picks up sensor data from the physical asset and computes important parameters which are difficult or impossible to obtain using physical sensors. These additional data sets provide the engineer with an unprecedented insight into the process and allows for an enhanced optimization. As the model enables you to predict the future trends, it can help in predicting future failure possibilities. And the downtime prediction can help you with planning. Companies can leverage the power of digital twin to extend warranty offers, generate higher revenue based on database predictive analytics. So based on a survey which was conducted by Evaluesurf back in 2019, and the survey was essentially commissioned by Ansys, it is said that by 2025, the net value of industrial assets which will be under condition monitoring or which will have some sort of digital twin attached to them will surpass 1.65 billion US dollars. So there is a huge untapped potential for this capability in the industry. Now, the industry itself is not something which is new to this digital twin concept. The digital twin concept first came into being somewhere close to 1950, 1960. The first industry which was adopting this technology was the oil and gas industry. Of course, they have a lot of equipment which is in the subsea sector, which is below water, and you cannot send in divers or you cannot send in submersible submarines or vehicles to test this equipment, check the equipment, and maintain this equipment at a very short duration, regular interval. So you need some type of monitoring system to understand what is the condition of those systems down at the bottom of the sea is. And that is where the digital twin concept started from. And now we can see digital twin everywhere. We have digital twins in manufacturing. We have automotive industry adding digital twins to their car, especially in the EV sector. You have digital twins in building and infrastructures, typically in the HVAC areas, and in aerospace, you have digital twins. So if I have to give you an example from the aerospace, it is like think of an aircraft, a same Boeing or an Airbus aircraft having a Rolls-Royce engine operating one in North America, another one in Dubai. Both the engines will be operating the same number of hours, but the equipment will be open to different kind of environmental condition. Out here in North America, the weather can be wet, it can be snowy, but down there at Dubai, it will be sandy. So there will be different kind of wear and tear which will take place. And if a company has a twin model for these two engines, they will be able to understand which model, which kind of wear is taking place in which engine based on where the engine is located. And that way, the maintenance schedule for these engines can be separately created. The parts and equipment required for this engine, for the engine to be in operation as long as possible, can be set up much more easily. So that is where the predictive power of digital twin helps. And the same can be done for any of this thing. I mean, it can be as small as an air conditioning system, which is at our home, or it can be as large as an important engine which drives an aircraft. So in general, if I look at the key elements of digital twin, there are these four factors. The first is the possibility of generating operational data using simulation. This is where Ansys software specializes in. So we have Ansys software suite, mechanical, electromagnetics, and fluids. All these three flagship solvers can generate simulation data of high fidelity, and you can use that simulation data to generate reduced order models and deploy digital twin. Once these models are ready and the digital twin has been, or the reduced order model has been created, it can then be offloaded to third-party tools offered by SAP, PTC, Microsoft, or Rockwell Automation to perform additional tasks such as database analytics, data processing and collecting using IoT platforms, and managing of asset and infrastructure, for example, in a processing unit. So now the image that you see showcases the fundamental workflow of digital twin deployment and usage. The data from the physical asset is relayed by the sensor to the IoT system. So this yellow section that you see, this is actually in the cloud, or it's in the internet or in the server somewhere. Now the data is sent directly to the server and it's stored in the cloud. We have our Ansys Twin Builder tool, which is taking data from our flagship solver. So it can be mechanical, fluids, or electronics, or it can be a coupled system, so an FSI problem. All the data from the different simulation cases are imported into Twin Builder. The Twin Builder then exports the twin model, which is deployed in the cloud. Now you can see that this deployment phase is a dashed line. So once this twin model is deployed, the connection to this Twin Builder platform is severed. So there is no connection anymore over here. Now this twin model will be able to access the sensor data, which is coming in live from the equipment, process that data, and then give out insights about this, what is happening inside this system. All the data is stored in this database and can be visualized using a dashboard. So if I have to give you an example, let's take an example of an electric motor. The electric motor sensor is sending in data of how much current the electric motor is drawing. Based on that current draw data, you can create a twin model, which can give me the temperature of the coil of that electric motor. So the twin model takes in the data, the input data for the twin model is the current draw. The output data for the twin model from the twin model is the temperature of the coil of the system. And now in this cloud system, you have both the sensor data, which is the current, and the output from the twin model, which is the temperature of the coil, which can be then visualized in a dashboard. And that will help the engineers to take the next logical step to improve the process. Now we will look into how we can build a digital twin. So before doing that, I will go through our basic solution, which is called the Ansys Twin Builder. And there are 4 things that I want to highlight over here. One thing, the first one being, this is a multi-technology platform, and we have the possibility to couple different modeling languages into one. So you can see over here, there is a library which is available. There is possibility of third-party integration. There's possibility of integration with our flagship tools, and there is also embedded software integration. It contains the capability of extracting a reduced order model from these large-scale simulations that we do. So this is the second big highlight. The third one is this is an open platform, so you can bring in, like I said, outside data files, or you can bring in models which have been created in MATLAB. You have created models in C, C++. You can bring that in to Twin Builder to attach them to your current Twin Builder 0D models. And last but not the least, it has the ability to deploy these models that you create using Twin Builder into a cloud or edge platforms, that is the IoT or edge platforms. So the full picture of the digital twin architecture is, as you can see in this slide. So we have the validated Ansys physics. This is our flagship solver. Then from this flagship solver, we can generate a lot of data, case and data files in general for fluids. You can extract reduced order models from this large case and data file. So when you extract reduced order model, a GB, a case and data file, which is probably 2 GBs, will be extracted into something which is in a couple of KBs, because you are not capturing the, if I have to give you an example with respect to physics, you are not capturing what is the turbulence parameter at every cell location, what is the temperature at every cell location. You're just capturing one out of them. So you are just taking a snapshot. It's like taking a picture of the simulation which is going by. So at 0 degree, 0 time, 10 seconds time, 20 seconds time, you take different pictures, a snapshot of that picture, and that is what creates the reduced order model. So that is why reduced order model is light and it can be solved faster. You can also bring in data from third party, and we integrate all of that within the Twin Builder platform. So if anybody has worked with Twin Builder, you know that Twin Builder has reduced order extraction capability for static ROM, which is with time, the solution is not changing, dynamic ROM, that is time variable solution, and LTI and LPV ROM. So this is linear time invariant type of ROMs. And you can also create 0D models over here. So if you want to create a feedback loop of a system, so if I have a tank and I'm filling in water into the tank, and there is a feedback system which is looking at the level of the tank and then asking the pump to either operate or stop, that will be a feedback loop. And that kind of loops you can create within the Twin Builder platform. Now, when you create such a loop, you are working with tanks, which is a multi-phase problem. You're working with pumps, which can be a multi-phase problem if you want to integrate it with cavitation physics. And you also have this electronics part where the feedback loop and the controller is working. You can create all of that. You can bring in reducer. You can develop reduced order model for the pump or the tank, and you can integrate that to the 0D model. The Twin Builder system has its own solver, and this solver is a transient solver, so you cannot solve anything in steady state. It's always based on time. And you can integrate all of this, solve this, look at how your reduced order model is behaving under a full integrated system. In this case, the tank of water, whether the controller is able to control the pump, and the pump is able to deliver the right head so that the tank is kept at a certain level all the time. Whether that specific parameter or that specific necessity is being addressed. Once you are satisfied with the operation of the reduced order model, then you can deploy the reduced order model. You can deploy the reduced order model either to an IoT platform or an edge platform. Edge platforms are generally chips which can be deployed on the hardwares. IoT platforms are cloud platforms. We also have Twin Deployer system, which can help you do Python integration to your in a home built system. So if you are working outside our digital twin platform, you can use Twin Deployer to generate your own Python code, develop your own graphical user interface, and other Linux compilation services that are necessary. So this is the full picture of the solution architecture. Now, what is a reduced order model? I have been talking a lot about reduced order model, but in general, if you think about it, it is a compressed version of a 3D simulation model that preserves the essential behavior and the dominant effect. So if I look at the image over here, what is happening is, with respect to time, I'm changing the temperature in this small inlet, and there is mixing that is taking place. In Fluent, if I run this case, so this is a transient case, and if I run this case, it will take over 3 hours on a 12-core system to complete the whole system. Now, from the case and data files that I generate over this 3 hours of time, I can capture snapshots of what will happen if the temperature is at 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, and then 100 degrees. I captured the final solution file for each of that input temperature and then club them together to form the reduced order model. And when I run this reduced order model, which is down here below, you can see that the reduced order model runs into real time, and the solution data that you see over here. So if you look at the qualitative comparison, if you compare the solution qualitatively, that is the temperature and how the mixing looks like over here downstream, you will see it's pretty accurate. And that is the power of reduced order model. The ROM solution is accurate. It captures, it keeps the fidelity intact, and it is instantaneous. So if you want now use this reduced order model and connect it to a system which is running live. Say, for example, this is a pipe, this is a mixer which is actually running in your experimental system or in your process plant, and you want to know what is the instantaneous temperature at this point. You can either have a temperature probe over here, or you can also deploy this reduced order model to see the way the temperature is going downstream, how the mixing is taking place, what will the bulk temperature at the outlet. And as you can see, a 3D plot or a 2D plot, cross-sectional plot of this data. The operator who is working on that system has a much higher understanding of the system, what is going on. And because he has a higher understanding of the system, he can now make better decisions. So that's the whole point of having this reduced order model. It provides you with much more data than you would possibly have with just sensors, and helps you take better decisions, if at all there is one. The ROM, as we said, how the reduced order model is extracted, the basic numerical technique which is used to generate this reduced order model is singular value decomposition. It's a matrix decomposition method where you capture the parameters which you are changing and the data which is of interest to you. You set up a matrix and you decompose the matrix into 3 parts. 2 of them will be identity matrix and 1 will be the matrix of the modes. And then you try to reduce the number of modes in that matrix to kind of reproduce the initial matrix of the solution data. And since you're reducing the number of data, effectively the reduced order model becomes smaller and smaller. But we have to be very careful about how much we reduce it, because if you reduce the number of modes too much, your error per solution will increase. If you increase the number of modes by too much, your reduced order model will become bulky. So there is always a very balanced point which needs to be found out, and that is effectively done based on the validation of the reduced order model against a calculated solution. So we will take a look at that at a later point. But in general, what we do is we create the training data that is using our 3D solver. We store the data and we extract the reduced order model using Twin Builder. There is also the scale. You can see it can take hours to days to generate the data. It only takes a couple of minutes to extract the ROM. The ROM size is typically in megabytes or kilobytes, not more than 50-60 megabytes at least. And then you consume the data. Now, since this is a very small system, the data which is computed by the reduced order model is instantaneous. So you can connect this data to a live stream which is coming in, and this ROM will still be able to give you an output at the same frequency rate at which the incoming data is coming in. So that is why we can deploy it for real-time monitoring of any systems. So now we effectively jump into process equipment. The first one is the most important process equipment which we see everywhere. This is the heat exchanger. The heat exchanger that I'm going to talk about is a shell and tube type heat exchanger. It has a diameter of 1.25 meters, 6.25 meters long. So you can see the dimensions are almost good enough for any industrial case. It has 96 tubes and 4 baffles to it. So the case file which was created, the mesh file which was created for the calculation has 6 million polyhedra cells and 3 boundary layers close to the zone. So this is not important, but just to give you a idea about the scale of the system that we are happening right now. You can generate a lot of different kind of data from different solutions. So what I show you over here, this is the deformation of the baffles generated using mechanical. This is a result which is showing the fouling in the heat exchanger, again generated using Fluent. This is the corrosion because of carbon dioxide presence in the system. So this is again CFX or Fluent data. So what I want to highlight over here is you can bring in data from multiple physics platform, and then you can club them together within Twin Builder to give what will be the corrosion rate like. If the corrosion rate is like this, what will be the buckling value will be, what will be the deformation value will be, what will be the stress value will be under different load conditions. In this case, we have already the case and data file for the temperature distribution inside the heat exchanger. And now we are trying to extract the reduced order model for the temperature distribution. So we open the static reduced order model builder. You will have to capture the snapshots. So this is the training data. This data is coming from our case and data files. So we have extracted a snapshot from each case and data file, and that snapshot has been loaded. So you can see what is the input data for the reduced order model. This is the mass flux, what is the tube temperature, what is the shell inlet temperature. Based on these three input parameters, we will be able to find out what is the temperature distribution throughout the system. You can also find out different things like pressure distribution, pressure drop, etc. So you can select on individual parameters to see how the distribution looks like. Once you have selected, now what we are doing is we are selecting the number of data points or the number of snapshots that will be used to train the reduced order model. So in order to generate the reduced order model, you will have to give it some parameters, some data sets, right? So these are the data sets. So you can see out of 24, I am asking the system to use 22 data sets, and I will use the rest of the 2 data sets for verification of the reduced order model. So it reduces, and then the system says that there is this whole data set can be represented by 22 modes. If you look at this curve, these are the number of modes that the maximum number of modes that are necessary to represent this full data set. So you can see there are 24 systems and there are like 24 modes that is. But the system has also computed that in order to represent this whole system using sufficient accuracy, in this case, if you want to represent the system with just 0.6% deviation from the actual data, you can work with 4 modes. So using just 4 modes in place of 24 modes, you are effectively reducing the size of the reduced order model while conserving the fidelity of the solution. And then once we select the mode, we can also change the mode, but as you increase or decrease the mode, the values change, and you can see what is the error based on how many modes that you have selected. Once you are satisfied with the setup of the reduced order model, you can then build it. So you can see the building takes only a couple of seconds. So once you have created the reduced order model, you can see below is your current ROM. And at the top, you have the reference initial data, which is coming from the 3D solution. So I know that the reduced order model has 22 data sets that I've used to train this data. So I will now select data set number 10 and 12 to do a comparison between my reference data and the current ROM, and it will showcase the difference. If the difference is within a certain limit, let's say in this case, it is within 1 degree Kelvin or 10 degree Kelvin based on what my requirement is, I will say that I have validated my reduced order model and I will move to the next step. So you can see that it has selected number 12. Reference data goes from 467 to 300 Kelvin. This data also goes from 467 to 300, but effectively there are sections where you have differences of around 39.6 Kelvin at locations. So if this is good enough for somebody, say it is within your acceptable limit of error, you can move ahead to the next part. At this point, we are exporting the reduced order model, and now you can see that I'm changing the mass flux. So I'm changing the input conditions now. and I will instantly get what the condition will be inside for the temperature. So I'm changing the shell temperature and we can see how the output looks like. We can also scale so that the temperatures are better visible. You can create dataset points at different locations of interest. And you can also create integral data, let's say average across one plane. And export the reduced order model to Twin Builder, where it can be visualized. Like so in Twin Builder, it will come in like this as a panel with points where you can add input data. And then there will be a point which will give out what is the temperature at a specific point and what is the average temperature at, let's say, the outlet. From here, we can now add. So now I have added input to the Twin Builder model. So what I'm doing is I am ramping up the mass flow rate using a sinusoidal curve. I'm ramping up changing the value of the tube temperature using a ramp. So there will be step inputs in this case. And also I'm changing the inlet temperature using step inputs. And this pulse is nothing but I am trying to capture the view at a certain frequency. So this pulse will send out a 0 or 1 value. 0 value says do not capture the data. 1 value says capture the data. Capture the data means it will take a snapshot of the solution, how it looks like. And at the same point, it will give me an output. You can set up the ranges. You can set up the name. You can post-process the data in Twin Builder GUI directly. And you can request for an analysis. You can see how fast the analysis is. So it's running for time. And you can see how this thing is changing with respect to time. You can also plot the data for a probe location 0 over here, and you can see how the temperature has changed at that location for the input data that I've given. So now you have to understand that this input data is right now data which I have created, but this can be very well online system. So a sensor data which is coming in directly from the sensor, going into the reduced order model. And as soon as the reduced order model receives that sensor data, it's able to give you how the temperature distribution looks like inside the heat exchanger and what is the temperature at any physical point where I have created, how the temperature distribution is, how the temperature profile looks like at that point. So this data was not there previously, and this essentially is the virtual sensor. So this sensor is not present in my original case, but now I have this extra sensor data, which is coming from my simulation. So that's the virtual sensor. Till now, I was working with the reduced order model, and now I create a twin. So twin effectively is we are wrapping this ROM into a package so that it can now also be connected to a third-party system, which is outside Ansys environment. And then it's exported like this. This can be exported to disk so that you can carry it anywhere or import it at a computer where you do not have access to Ansys licenses or you want to integrate it to something else, or you can export it and deploy it using an edge system. We exported the twin as a web platform, and in the web platform, it looks like this. So this you can see is open in Chrome, and you are pinging one IP address. And when you look at the IP address, the IP address will, this web page will come up with how the measurement data looks like, what is the input data looking like. In a minute, when it scrolls down, you will also be able to see how the temperature distribution in the system is, and you can also interact with this 3D data. So finally, in the summary, we have a real equipment where we have sensor data. We have sensor input data coming in. going into the virtual equipment, which is our simulation model or reduced order model. In this simulation, we can create virtual sensors for fouling, stress, remaining life. You can create the reduced order model, which gives an output for these values, and we can deploy the digital twin the way we want it. We can create simple twin model and export them. We can create web pages, or we can design our own GUI. Next will be this is one of the most important equipment. Next is another way of applying digital twin to find out the reactor blend time. So this is again a case which was studied, I think 3-4 years back. It was also presented in Ansys user conference. So what we want to do over here is a basic continuously stirred reactor system. And we want to see that if I have a species or a chemical which is injected in this portion or in this portion, how much time does it take to get uniformly distributed in the system? It's something which is very important in the chemical industry, and the blend times essentially mean a lot in terms of the usage in process. So what we do is with it is we created 40 design points and we solved it using 48 cores. Each design time will take typically 36 minutes. So in average, it took 24 hours to create the 40 design point case and data value. You export this case and data value in the form which is acceptable to Twin Builder. In the Twin Builder model, now you have data which gives me what is the species distribution at the specific location. So I am patching the species over here, and then I'm looking at how the species distribution looks like at different section. And when I look at the species distribution with respect to time, I'm looking for this time where all the concentration converges to a same value. So this effectively means the concentration of this species which has been injected at this point is now uniform throughout the vessel. So I get a design point distribution for the blend times for different operation, like this RPM, RPM rate at this case, and I can create a matrix for this. So we use this learning data points. The red ones, the blue ones are the learning data points. In this case, we have, let's say we have 40 data points available. We are using 80% of the data points for creating the reduced order model, which I'm calling as learning. Then I'm using the rest of the 20% for validation. So when we compare the learning data point, learning solution to the validation solution, you can see how the comparison looks like. It's very close to each other. So this is another example of how we can use reduced order model to compute the blend time in a reactor. So in this case, what we are doing is we are looking at a hydrogen combustion system, and the digital twin should tell me what is the exhaust gas composition like, how much NOx it is generating, how much SOx it is generating, so nitrogen oxide and sulfur oxide. And if I change some input parameter, in this case, how much fuel I'm injecting, what will be my flame length? And it can also compute what will be the heat distribution like. So this is a very good example of a simple reduced order model and how it can be used in day-to-day platform. So you can see that I'm changing the regulation real time for the fuel gas, and you can see how as soon as the H2 injection started, how the other parameters started changing. In conclusion, if you look at digital twin, it unlocks the significant top line and bottom line for any expensive asset failure. It is physics based, so you are keeping the physics intact. You're not changing it just by playing around with numerics. Customers can quickly build it, validate it, and deploy it. And the very fact that you are validating the reduced order model gives a huge amount of confidence on the solution. And the additional data which is coming from the field data can also be added to this digital twin to make it better and better over a period of time. So it's not that once you create the twin, it cannot be improved any further. As you get more and more data coming in from the field, you can augment the data to the current twin and you can improve it further.